Here's a little bit of a change to our Lenz's Law tube video. I'm going to add a little bit of mass to it, which gives it a different terminal velocity. So, doing it, get it set up here. All right, so first of all, here's just the large magnet. I drop it in. 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I'm going to put this mass on it. This mass has, it's got some metal in it. It's got some iron in there apparently. Watch what happens now. You can see it. 1, 2, 3, 4. And you can see it even when it goes in, that there's a significant speed up there. Now let me get a little bit closer so you can see this. Hard to do with only one hand, but here we go. Ready? There it is. Okay, and now with the object on top. Significantly faster. Well, let's talk about what we do and do not know here. Obviously, when there was more weight on the magnet, there must have been a greater magnetic force holding it backwards. Now, as for, and also you notice that when there was a mass on it, there was a greater terminal velocity. It was moving faster. Now, how would we calculate that force? Because we have a couple of calculations. FB, our magnetic force, equals QVB, but we don't have a particular charge. We have BIL, but we don't have current in a wire, so I'm not really sure where to go on that. But what I can say is that we should be pretty confident that this is some sort of Lenz's law, or sorry, Faraday's law, where a greater change of flux causes a greater current. So my guess is that in order for there to be a greater magnetic force, there has to be a greater current going around the tube. Well, this is moving faster, so there's a greater change of flux as it's going through. Same magnetic field, going faster, so a greater dphi/dt, and that equals a greater EMF, which for the same resistance equals a greater current.